Okay, I thought I would do a couple of problems from this chapter involving change of basis. What I recommend with this chapter to really understand what's going on is always go back to first principles. Okay? Because you can understand this in terms of what's happening to vectors. And there's one key formula that you use again and again and again that I want to bring out in this video. So find bases such that this matrix represents the identity map with respect to those bases. Okay, so we're dealing with three-dimensional vector space. Actually, we're dealing with R3. And we know that we can represent vectors in terms of any basis. So we want to translate between two different bases. So what is this talking about? So when he says the identity map with respect to two bases, we can represent any vector in R3 as in terms of a basis. So let's say B is a particular basis, vectors B1, B2, and B3. So I can represent any vector in R3 this way, x1, b1 plus x2, b2 plus x3, b3, where x1, x2, x3 are numbers, okay? b1, b2, b3 are the basis elements, right? Now, what we're saying is we can represent that same vector in two different ways. We can represent in terms of b1, b2, b3, or we can represent in terms of another basis, d1, d2, d3, and those would have three different coefficients. Okay. So when he's talking about representing the identity map, he's saying that in fact, there's a matrix that relates the coefficients with respect to the B basis and the coefficients with respect to the Y basis. It's the same vector, identity map, same vector, but we're relating the coefficients. Okay, so here what they're saying is that the identity map from basis B to basis D is expressed by this matrix. It means I can get the coefficients for the D basis from the coefficients from the B basis by using this matrix. That's what it means. Okay, right. Now, I want to relate this matrix equation to this vector equation, and that's the key here. This vector equation can be written as a matrix equation, right? These b1, b2, b3 are column vectors. x1, x2, x3 are numbers. This vector here can be written as b1, b2, b3, this matrix consisting of the column vectors of B times this column vector of the coefficients. Very key equation, comes up again and again. Relates the vector equation to the matrix equation, right? So this expression here, this vector expression, can be written as this matrix equation. Same over here. This vector expression here, y1, d1 plus y2, d2 plus y3, d3, can be written as the column vectors d1, d2, d3 times this column vector consisting of the coefficients y1, y2, y3. Okay. Now, once you have this matrix equation, it's an elementary matter to convert this to an equation that relates y from x, right? I just take the inverse of this matrix and put it over on the left-hand side, okay? But what we have here now is the relationship between the coefficients x and the coefficients y. So in fact, we can identify this matrix here, this 3, 1, 4, etc., with this product here. Right? So we can relate this here. Let me just use a different color just to point it out. We can relate this matrix here with this matrix here, right? It's the same matrix. Okay. So all I need to do is choose B1, B2, B3, D1, D2, D3 to get this matrix. Now, there's many ways to do that. The easiest way is to simply choose my D1, D2, D3 as the column vectors E1, E2, E3, the elementary basis vectors, which would make this vector, this matrix, the identity. And then B1, B2, B3 would simply be the columns of this matrix. No, that's not the only choice. Another choice would be I could choose the column vectors D1, D2, D3 to be the columns of the inverse matrix, and choose B1, B2, B3 as the elementary basis vectors. So there are many different ways to do this, but of course the easiest way is the first one. But just to recap, the way I was able to analyze this problem was to write down what does it actually mean to change bases in terms of a vector equation. and then rewrite that vector equation as a matrix equation. Okay? And you can actually do all the problems this way by analyzing according to first principles. Okay, now a second problem from this same set. All right. Let V have bases B1, B2. Let me make this a little bit bigger so you can see it. Okay. All right, let V have bases B1, B2, and suppose W has the basis D. All right, so keep this in mind. Two different vector spaces. The first vector space has two different bases, and the second vector space has one basis. Where H is a function from V to W, find the formula that computes rep B2DH from rep B1DH. Now, H is a linear map, we understand from the chapter. Okay. And you know that you can represent linear maps with respect to bases. So you're trying to find one representation with respect to one domain basis, B1, and change that to another domain basis, B2. So let's write that out in terms of what happens to vectors, right? So when we talk about representing a vector with respect to basis B1, that means we have a linear combination like this. So I'm using this superscript 1 to indicate basis B1. So B1 through B1 superscript 1 through Bn superscript 1 is the basis for basis B1. Right? Now, H acts on a linear combination of this basis vectors to give me a linear combination of bases in the codomain, basis vectors in the codomain. Okay, so this is expressing this linear relationship, right? And the definition of rep B1DH is the matrix that relates the coefficients in the domain to the coefficients in the codomain. That's the definition of rep B1D of H. It's that matrix. There is a matrix relationship between the coefficients. Now, let's think about what this means. We know that H is a linear map, so we can decompose H of this linear combination into individual components, right? This is just a linear combination, so we're using the linearity property of H. Right? Now, we can write this now as a matrix equation, just like we did the other equations here, right? This is x1 times this vector plus ... plus xn times this vector. So that means that I'm taking x1, I'm taking the column vector x1 through xn and multiplying by these column vectors, okay? This is the same technique I used in the previous problem. Right? So in fact, this matrix rep B1DH is equal to the matrix consisting of these columns, where HB1 of D is the representation of H of B1 with respect to the basis D. Okay, all right. Because this HB1 we want to identify that with the vector in the codomain that B1 goes to, and we want to represent that in terms of the basis D. Okay, so this is how we can understand rep BD of H. The column vectors are H of the basis vectors B1 expressed in terms of the basis D. All right. So now let's look at B2. B2 is done the same way. Right? If I want to take H of some linear combination of B2 basis vectors, I'm going to get some linear combination of D basis vectors. Now, suppose we could rewrite this combination of B2 basis vectors in terms of B1, right? Suppose I could write, kind of translate from basis B2 to basis B1. There's a relationship between this linear combination and a linear combination in terms of basis vectors B1. We know that any vector in the domain can be written in terms of either basis, right? So there has to be a translation that enables me to rewrite this linear combination in terms of basis B2 as a linear combination in terms of basis B1. But if I could rewrite this linear combination in terms of basis B2 in terms of basis B1, well, I've already solved that problem, right? I can translate this into the map H simply by using my previous map, right? I know that when I apply H to this vector here, that's going to give me coefficients y1 prime through yn prime in terms of basis vector D, and they're related by the representation map. Okay, so the strategy here is to go from basis B2 to basis B1, and then once I have the vector in terms of basis B1, I can translate that. I can apply H to that by using the representation matrix that I already have that relates B1 to D. Okay, so the point is, the problem is reduced to translating from basis B1 to from basis B2 to basis B1, right? But that's what we have here. We want to rewrite this linear combination in terms of basis B2 as a linear combination in terms of basis B1. And I'm using the same trick of rewriting this vector equation as a matrix equation. All right, so I want to go from x1 primes to x1 double primes. I'm sorry, I want to go from the x prime coefficients to the x double prime coefficients, so that then I can go from the x double prime coefficients to the y prime coefficients. Okay, all right, but I can see right here that if I want to get the double prime coefficients from the prime coefficients, I just multiply by both sides of this equation by the inverse of this matrix. So altogether, if I put those things together, I have y1 prime to yn prime equals rep b1d times this vector. This vector is equal to this inverse matrix times this matrix, and then I multiply that by x1 prime n. So this here, this equation here, puts together this equation here and this equation here. Okay, all right. Now, what's another way to write this equation here? Well, what are we doing here? We're going from the coefficients x1 prime through xn prime to the coefficients x1 double prime to xn double prime. Okay, so it's the same vector. We're just taking the different we're relating the different coefficients of the same vector, right? We're identifying this vector with this vector, just we're representing it in terms of different bases. Okay, so it's taking the representation of the vector in the B2 basis to the representation of the vector in the B1 basis, right? Since it's the same vector, that's simply the identity map. And I'm taking the representation of the identity map in basis from basis B1 to basis B2. So this matrix here is simply the identity, the representation of the identity with respect to the bases B1 and B2. So you can write it that way. But you can think about it this way. The way you actually get that matrix in practice is you write down your basis B1 and then take the inverse and then multiply it by the matrix consisting of the column vectors from B2. Okay.